giving me this opportunity to give a talk here. And I was told that one of the subjects of this workshop is quantum KMM theory. And I got the mission to give this talk this morning. And how can I say, but I'm not really an expert on the KM theory, and I'm not, how can I say, the right person to give an overview talk on this KM. But on the other hand, we have some nice results on the quantum version of KAM stability for finite dimensional quantum systems. And this would be a nice, how can I say, starting point for the discussion today. So let me try to focus mainly on the result we got recently for finite dimensional systems. Okay, so the KM theory concerns the stability of the integrable systems. And the popular example is the stability of the solar system. And what if this system is perturbed? It is still robust, or it is just destroyed. And there are many works have been done on this issue, more than 70 years, 60, 70 years. And so there is seminal results of the KM theorem in classical mechanics. And so let us consider some integrable system, and you find D conserved quantities for D-dimensional classical system. And you go to the action angle variables, and we have many conserved quantities. J are the conserved quantities. And if this system is perturbed, then the conserved quantities for the unperturbed system is no longer conserved quantities. But anyway, somehow the okay, so the unperturbed system, the dynamics of the unperturbed system is can be described by this kind of torus. And even under the perturbation, this torus is somehow preserved under certain conditions. And the stability of the system is guaranteed. Okay, so, and we want to discuss the quantum version of such a KAM stability issue. And, but I mainly focus on the KAM stability problem for finite dimensional quantum systems. And we have some results, and I would like to tell you the results. And we are going to characterize that there are two types of conserved quantities. Some conserved quantities are fragile. So if you add some perturbation on the system, the conserved quantities, such fragile conserved quantities are no longer well conserved. But on the other hand, there are another type of conserved quantities. They are very robust against the perturbation, and they can be somehow more or less preserved for any long times. That's the result of our work. And this somehow is a analog of the quantum version of the KM theorem. Okay. So, and this result is based on the adiabatic theorem. And I think the adiabaticity is one of the subjects today. And in particular, so this result, cum-like stability result, is based on the eternal adiabaticity of the adiabatic evolution of quantum systems. And so the adiabatic theorem holds for arbitrary long time. That's why we call it eternal adiabaticity. And this allows us to prove the long-term stability of some conserved quantities for finite dimensional quantum systems. Okay. So let me start with a very simple recapitulation of the adiabatic theorem in quantum mechanics. Okay, so if you look into some textbook, you find an adiabatic theorem, and usually it is discussed for the time-dependent Hamiltonian, the evolution of the time-dependent Hamiltonian. And we say that we drive the Hamiltonian very slowly. Of course, the meaning of slowness is not really how can I say, precise. But anyway, we say that we drive the Hamiltonian very slowly. And suppose, for instance, we have many discrete instantaneous eigenvalues of the time-dependent Hamiltonian. So you think of the spectral projections of the time-dependent Hamiltonian, and you find the instantaneous eigenvalues and instantaneous eigenprojections. And the adiabatic theorem says that if you start from some eigenstate of the Hamiltonian at time t at time 0, then the system remains in the same eigenspace at time t, and with some error. Epsilon characterizes the speed of the driving, and this usually, if you look at the textbook proof of the adiabatic theorem, this adiabaticity holds for this time range. So epsilon is small, so it's rather adiabaticity holds for rather long times. But anyway, for certain limited time, this adiabaticity holds. Okay, so for instance, if you consider this kind of three-level system, time-independent three-level system, and this system has three eigenvalues, and as a function of time, they are something like this. So you see three red curves. They are the eigenvalues as functions of time. And suppose we start with the eigenstate 1, then you let the system evolve according to this time-dependent Hamiltonian. And the adiabatic theorem says that the system more or less remains in this, more or less follows this, the eigenspace number 1. Of course, there are some leakages from 1 to 0, 1 to 2, and so on. But anyway, the leakage is bounded, is estimated to be of order epsilon. That's the adiabatic theorem. In
this example, what would capital T be?
Capital T is just some order 1 time. And epsilon is small, the dimension is constant, much smaller than 1. Yeah, and you drive the Hamiltonian from 0 to time capital T. Okay, but in this talk, let me focus on the constant time-independent Hamiltonian. So I have some unperturbed Hamiltonian H, and it is perturbed by some constant perturbation. And this also reveals this adiabatic theorem, because, for instance, so if you go to this how can I say, interaction picture, rotating frame with respect to the perturbation, then this evolution under the constant independent Hamiltonian is equivalent to this evolution according to the time-dependent slowly varying Hamiltonian. So that's why, the problem above, how can I say, is also related to the adiabatic theorem. And I focus on this adiabatic theorem for the constant time-independent Hamiltonian system. Okay. Now then, so let us consider the spectral representation of this unperturbed part of the Hamiltonian. So you have eigenvalues, spectral projections. They are orthogonal to each other. I just focus on the unitary evolution, Hamiltonian cross systems. And we have some distinct eigenvalues. So I'm just focused on the finite dimensional system. So the spectrum is just discrete. And okay, so what is adiabaticity? So this unperturbed Hamiltonian has some eigenspaces. The eigenvalues can be degenerated, but anyway, we have some eigenspaces. I assume that we have m eigenspaces, and this perturbation provokes some transitions among the eigenspaces. But adiabatic theorem says that this such a leakage out of the eigenspaces is, how can I say, limited, bounded by order epsilon for some time. Okay. So naively speaking, so we have some perturbation on the Hamiltonian H, and this perturbation would accumulate over time, and the dynamics of the system under perturbation can become very different from the original unperturbed Hamiltonian. So we can try to estimate the distance between the perturbed dynamics and the unperturbed dynamics. And you can easily show the upper bound on this distance, and it is linear in time. So
Is
this
this independent of the norm of H?
Yes.
Yes.
independent of the normal H. Yes. And so this somehow tells you that the effects of the perturbation accumulates in time. But this does not say that the adiabatic theorem does not hold. You can do more sophisticated estimates on the leakage out of the eigenspaces. And if you apply the standard adiabatic theorem, for instance, you can find a proof of the adiabatic theorem in quantum textbooks on quantum mechanics, or maybe you can look at this seminal paper by Kato, published in 1950. Then you can prove the adiabatic theorem for this system, and you can prove this bound. So now here, this is the true evolution under perturbation. The Hamiltonian H is perturbed by the perturbation V. And now Vz is defined by this equation. So this Vz is the projected version of the perturbation, where P's are the spectral projections of the unperturbed Hamiltonian. So this modified perturbation Vz does not induce any transitions among the eigenspaces. So this evolution, H plus epsilon Vz, this describes a kind of adiabatic evolution. So the system can evolve inside each eigenspace, but this dynamics does not provoke any transition out of the eigenspaces. So this describes a kind of adiabatic evolution, and we can estimate the distance from such an adiabatic evolution of the true evolution under the perturbation. And I'm not going to show you the proof of this adiabatic theorem because this becomes rather technical, but I can show you if you like. And we can get this bound. So what does it say? So first of all, for the adiabatic theorem, eta is important. Eta is defined by this equation. So this is just the minimal spectral gap of the unperturbed Hamiltonian. And the bound is proportional to epsilon. Epsilon is the strength of the perturbation. And you find time here. So before you have time t here, but now we have time t here. And so this means that the coefficient of time is epsilon squared. So that's why this distance remains order epsilon up to time of order 1 over epsilon. And if epsilon is small enough, so it's rather long time, for a long time, the distance from the adiabatic evolution remains small. That's the standard adiabatic theorem.
I don't understand the M though.
Sorry. M is the number of distinct eigenvalues of the unperturbed Hamiltonian. So the number of blocks. Okay, thank you. Now, by the way, this Vz, I called it Vz because this projected Hamiltonian is nothing but some people call it a Zeno Hamiltonian. So it is related to the quantum Zeno dynamics. So the quantum Zeno effect means that the transition from the eigenspace to other eigenspaces are prohibited. That's a quantum Zeno effect. But still, inside each eigenspace, the system can evolve, and such a dynamics is described by this projected Hamiltonian VZ, and such a dynamics is called quantum Zeno dynamics, and this projected Hamiltonian is called quantum Zeno Hamiltonian. Okay, that's why I called it VZ, but anyway, this is just a standard adiabatic theorem.
Sorry.
Yes.
What happens for t equals 0? So you don't get 0 on the right hand side.
Uh-huh. This is just an upper bound.
Okay, sure.
Yeah.
So it's okay.
The estimate is rough because I used many, how can I say, for instance, triangle inequality and so on. But if I go back to the original expression before the triangle inequality, yes, I get 0. Thank you. Okay, let's look at some simple examples. This blue curve represents the distance between the perturbed evolution and unperturbed evolution as a function of time. This is not an upper bound. I just plotted the distance as a function of time. So this evolves like this. And here I chose epsilon 0.5. So you see, so the distance becomes of order 1 at time 10. That's the so yes, this is the okay. This is the accumulation of the effect of the perturbation. But if you go to the adiabatic theorem, so this delta z, the distance between the true evolution and the adiabatic evolution, and you get this green curve as a function of time. This is just a distance, and you see the distance remains small of order epsilon. So now I chose epsilon 0.1. So that's why, okay, so here, this is the order of the error is like 0.1 because of epsilon is 0.1. And the distance remains 0.1 up to time 10 to the power 2. Okay. And I realized, or maybe you already realized, that this Zeno Hamiltonian is just first order perturbation. So what you learn in the undergraduate course on quantum mechanics, you solve some perturbed Hamiltonian perturbatively, and you get the first order correction. So this VZ is nothing but the first order correction to the in the perturbation in the theorem. And so this green curve gives you the, how can I say, error of the first order perturbation. So then if you can go to the second order perturbation, then you get this distance. And so if you go to the second order, you can make the valid time range longer. So now, so the distance remains order epsilon up to time 10 to the power 3 for epsilon 0.1. And actually, for instance, in the field of quantum optics, this second order perturbation is called adiabatic elimination. And this is often used in the modeling of quantum devices, for instance, superconducting qubits and so on. So this, how can I say, validity of the model will be, long-term validity of the model will be important for the quantum technologies. Okay, so now, so we went on to higher orders of the perturbation. And if you go to the third order, you can make the valid range for the approximation longer. You can go to the fourth order, fifth order, and we reached infinite order. Okay, so actually, so this red is, I call it eternal. It means that the distance between the true evolution and the perturbation and the approximate effective adiabatic evolution. Actually, this is the full order perturbation. So you can resum all the orders of the perturbative corrections. And this gives you the eternally valid effective model approximation. So
can you write this down, this V add?
Yes, yes, I will tell you, yes. So this is basically the full order perturbation, and you can resum all the orders And this gives you the adiabatic theorem valid for any long times, for arbitrarily long time. That's one of our results.
Why is it the error not zero if you sum the whole thing?
Yeah, so you have perturbations, so you cannot avoid the leakage out of the eigenspaces. We cannot avoid.
It's simply there.
Yeah, simply there. But anyway, so, if you study the standard adiabatic theorem in a textbook, so we learn that the adiabatic theorem holds only for a limited time, for a finite time. But for this constant Hamiltonian case, the adiabaticity holds actually any long time, eternally. That's our result. Please.
Was there more there? You have more to ask. So I noticed that there's a lot of oscillations in that error plot.
Yeah.
Plot, and so those doesn't look like the bound is oscillating. Is there a way to? Is there a theory for how those oscillations in the distance are going?
Oscillation. So you see, this is
Maybe it's random. Maybe it's not a.
first of all, the horizontal axis is a logarithmic axis.
Okay.
So that's why I can say you see very radical oscillations, but if you go to the linear scale, you see some oscillations. And this is in general quasi-periodic oscillation. Yeah, that's the how can I say origin of the oscillations. And sorry, what do you want?
Yeah. So is there a way to account for that in the bounds? Has that been
Bound.
studied?
Ooh.
Because if you then take the picture off, there's there's upper bounds on those distances.
But anyway,
But
distance reaches to 2 is actually the maximum in the operator norm. So anyway, how can I say? Yeah. I don't know. Maybe I just obtained upper bound.
okay.
Yeah. We didn't capture.
Yeah, that depends on like how the eigenvalues, what the ratio is, if it's rational.
Yeah. And it's just a quasi-periodic oscillations.
So just to clarify my previous question,
Yeah.
so the point here is that this is an approximation that still leaves the eigenspaces intact.
Yes.
So if with that constraint, of course, there will be residual errors.
Yeah, right.
The exact dynamics doesn't do
Right.
that.
But the error remains epsilon for any long times. That's the non-trivial point. Thank you. Okay, so how we obtained this eternally valid adiabatic generator? So this looks very complicated and technical, but anyway, first of all, V infinity, this gives us the full order perturbative correction. And this is commutative with the unperturbed Hamiltonian. So if you recall the standard perturbation theory in a textbook, the perturbative series always respects the eigenspace of the unperturbed Hamiltonian. That's why any perturbative corrections do not break the block structure of the Hamiltonian. So this full order resound correction V infinity respects the block structure of the unperturbed Hamiltonian. So it is commutative with the unperturbed Hamiltonian. And actually, this is an original evolution, H plus some perturbation. And this is the resummation of the full order perturbative correction. We can show that they are unitarily equivalent to each other. So it is related to unitary transformation. So they share the same spectrum. And it is important for the eternal adiabaticity. And anyway, and this unitary transformation is close to the identity. And this is slightly different from the identity by some, how can I say, of order epsilon. Okay, this allows you to prove the eternal adiabaticity. So first of all, so this is, as I told you, this is just basically, essentially the standard perturbation theory you find in the textbook on quantum mechanics. And we learned that such a, how can I say, there is of course, a long history of the studies on the perturbation theory. And we found these articles in 1958, 1960. These papers studied, of course, very carefully the perturbation theory. And there is a recipe to find the resummation of the full order perturbative correction. And the recipe is the following. So please solve this operator equation or matrix equation for W. So it's a quadratic matrix equation for W. And once, so it is called a Bloch equation, but this Bloch is different from the Felix Bloch. But this Bloch is author for this paper published in 1958. So, but anyway, let me call it Bloch equation. So you solve this quadratic matrix equation, and we can solve it at least numerically, or sometimes you can solve it analytically for some specific models. And for instance, for 2-level system, 3-level system, 4-level system, there is a chance to get analytical solution to this quadratic matrix equation. And then you construct this unitary U by this rather complicated formula. Anyway, this allows you to perform the unitary transformation on the original Hamiltonian to the block diagonalized Hamiltonian. And this gives you the full order perturbation. And in addition, so we found that such a, how can I say, theory has been found repeatedly. And in the field of condensed matter physics, people call it Schrieffer-Wolff transformation to construct an effective model for some condensed matter system. And anyway, so this is what essentially we are doing, and so we can call it Schrieffer-Wolff transformation. And so now you know how to construct a unitary, and because of the unitary equivalence, I do not follow the derivation, but you can show that the distance remains epsilon for any long time. Okay. Then, as I told you, for the eternal validity or the adiabaticity, the isospectral character is important. So consider, for instance, two Hamiltonians, H tilde and AH, and suppose they are different by some epsilon or the epsilon, and you consider the spectral representations of H tilde and H, and we want to compare the evolutions generated by these two Hamiltonians. Okay, and basically you see the difference in the spectral projections, and you see the difference in the spectra, and you can estimate the distance by using the triangle inequality. And by the standard perturbation theory, the distance between the spectral projections is just of order epsilon. And on the other hand, the distance between these two exponentials of the eigenvalues gives you this sine function. And if E tilde and E are different, so if the two spectra are different, so this error can become 2 at certain time, and then this distance becomes of order 1. Okay, but on the other hand, if the two spectra are the same, they share the same spectra, you do not have this correction. This is just 0, and you get distance epsilon. So that's why in this way, the isospectral character is important for the eternal validity of the adiabaticity. Okay. Now, I would like to mention some previous works. Of course, there are many works related to quantum version of Kampf theory, and I just pick one among many. And this is by Scherer, published in 1995 or 1997, and he just followed the idea of Bogolyubov for the CAM theory in classical mechanics. So he just translated the CAM iteration procedure to quantum mechanics, and he got this result. So I'm not going to show you the iterative procedure, but he has some iteration procedure step by step. And the idea is basically to make the original Hamiltonian block diagonal by performing unitary transformation little by little. And after n iteration, he could get this distance like this. So the error becomes exponentially small. And some people call it a super convergent series. It's actually not really a series, but anyway, this so you see, this is more or less unitary transformation between the original system and the block diagonal system, but there is some error. So that's why this small error can accumulate over time. And in this way, you cannot prove the eternal adiabaticity. So, and in this sense, our result goes beyond this result, and we can prove the eternal adiabaticity. So the adiabaticity, by this strategy, adiabaticity holds up to time of order epsilon to the power 2 to the power n minus 1. So it's really long, but anyway, it's not eternal.
Sorry.
Yeah.
Isn't it true that there's a trade-off here? If you want to do something good for short times, you might actually not go for the eternal solution. Because I mean, if you just do your standard perturbation theory, that would be the best approximation for small times. But if you insist on having this eternally, then you'll pay a little bit in error for the small times. Is that correct?
But in order to get this result, I just used perturbation theory, and the error remains epsilon for any long time, not only for short times. Yeah.
But your error for small times could actually be worse than the straightforward second order perturbation or so.
Worse? I don't think so.
I mean, you may pay for the eternal nature of your approximation, having it not so good for very small.
I think error is anyway order epsilon, but the
Epsilon is fine, yes,
range of the validity becomes longer and longer if you collect a higher and higher perturbative correction.
Well, that's only upper bound for very small t. It could actually be better.
Yes,
That's what
right. Okay.
It could be with this new thing. It could be worse than the best you can think of. Right?
Okay.
Yeah, so it's not an upper bound, but it could be effectively better.
But it has to be, because if you
sure.
the series expansion,
Yes.
then for small values, that is the best approximation. So you have to pay for the small times a little bit.
We don't see this in the example, no? I mean, the plot that you had where you had the different orders, it seems like the higher order is already better also for short time.
Yeah.
It could be that the constants are different, but
of course, we are losing linear. It was very small time. It's
very
epsilon t.
small
It's
time,
epsilon
yeah,
t.
Yes.
So when t goes to 0, it goes to 0.
Yeah,
This is just the observation as before.
Right.
So you are losing that initial linear part.
Yeah.
But up to that, you are not losing.
Yeah. So
The constant is the same. So
if we limit, if we focus on the short times, then we can do better maybe. Yes.
No, this is great.
Thank you. Okay. So now I want to go to the robustness of the system. Okay, so the CAM theorem concerns we can say that the CAM theorem concerns the robustness of the conserved quantities, and robustness, in other words, the robustness of the symmetries of the system. Okay, so some physical quantity S, observable S, is a conserved quantity if it is commutative with Hamiltonian. So if S is commutative with Hamiltonian, And if you consider the Heisenberg evolution of the operator, this remains constant. That's the conservation law. And in other words, so this, on the other hand, is related to the symmetry. So if you consider the symmetry transformation generated by the conserved quantity, the Hamiltonian remains the same. So this is a symmetry. So you know that the conservation law and the symmetries are related to each other by Noether's theorem. And okay, and so if the Hamiltonian, please consider the spectral representation of the Hamiltonian, and you find the block structures, eigenspaces, and if S is a conserved quantity, they share the same block structure. So the conserved quantity has this block structure, respecting the structure for the Hamiltonian. And the Hamiltonian, in the case of Hamiltonian, each block has same diagonal elements, E0, E0, E1, 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 E2, E2. But on the other hand, the conserved quantity has the same block structure, but inside each eigenspace, it can have non-trivial matrices. Okay, that's the difference between Hamiltonian and the general conserved quantity, and this will be important in the following discussion for the CAM problem. Okay, so how this symmetry is robust against perturbation? That's the topic of CAM stability. So if the system is not perturbed, this quantity S is a conserved quantity, and but if it is perturbed, it is no longer a conserved quantity in general, and this might deviate from the initial value, some order epsilon. And actually, so error remains epsilon at least for time of order 1. So if you go beyond longer, then the error can accumulate, and the conserved quantity is more perturbed. Okay, indeed, we can show the distance between the initial value of the conserved quantity and the evolution of the conserved quantity under perturbation, so perturbed evolution. And I do not follow the derivation, but anyway, you can bound it by something linear in T. So this shows that at least up to time of order 1, the perturbed quantity, perturbed conserved quantity remains close to the original initial value. Okay, but if you go longer time, the conserved quantity of the unperturbed system can become very different from the initial value. Indeed, we can explicitly construct such a bad perturbation, and suppose you have some Hamiltonian, it has some block structure, and you consider some conserved quantity, so they share the same block structure, and suppose that inside one eigenspace, the eigenvalues of the conserved quantities are different, S1, S2, and S3. Let us assume that S1 and S2 are different, and there is some this difference delta. And so this breaks the degeneracy or the unperturbed Hamiltonian. And now we can consider this kind of perturbations. This provokes transition between two states inside an eigenspace. And you can compute this time evolution starting from some initial state, and you can compute explicitly. So this difference becomes order 1, for instance, at this time. Okay, so this shows you that in general, the conserved quantities are not robust under the perturbation. So if you go longer time, the conserved quantity becomes, like I say, very different from the unperturbed value. However, we found robust conserved quantities, and it is characterized by this formula. So if the conserved quantity is a function of the unperturbed Hamiltonian, then such conserved quantities are robust eternally for any long time. That's our result. So I do not follow the calculation, but anyway, and we can use our eternal adiabaticity result for this proof. And I consider this full order summation of the perturbative corrections. And we can prove that this difference, so S is the initial value of the conserved quantity of the unperturbed system. And if it is perturbed, the difference, there is some difference, but the difference is upper bounded by this quantity for any long times. So this shows you that this kind of symmetries are robust against perturbation, and this is in a sense an analog of the CAM stability. Okay, so let me summarize. But I told you there are two types of symmetries, conserved quantities. And first of all, the symmetry is a quantity which are commutative is Hamiltonian. So we can say that the symmetries are the elements or the commutant of the Hamiltonian. And there are two types of symmetries. So one type is fragile symmetry, and the other type is robust symmetry. And so if symmetry S is fragile, so the difference can become of order 1 if you wait for a long time, while the robust symmetry is characterized by this. So the robust symmetry is a function of the Hamiltonian, so it's an element or the double commutant to the Hamiltonian. For such symmetries, this quantity is more or less preserved over a very long time, actually any long time.
Should it not be enough if the V infinity commutes with S?
Pardon? V?
If your eternal perturbation V infinity,
V.
that commutes with S, that should also be sufficient.
V infinity commutes with the
If it does, then with a symmetry.
Yes. That's the
also
point.
get something.
Yes, yeah, that's the point in the proof. Yes. The commutativity is important. Okay, so let us look at some simple examples. So I consider 4-level system, and I consider 2 blocks, just 2 different eigenvalues, and I chose perturbation V just randomly on a computer, and I chose randomly some observable, not necessarily conserved quantity, and I chose randomly initial state for the 4-level system. And for any observable M, you can always decompose it into 3 contributions. So the one is the robust symmetry, and the other one is fragile symmetry, and the rest is the off-diagonal component of the physical quantity. And this is the evolution of those 3 quantities, or those 4 quantities, and as a function of time. Okay, so the yellow curve represents the evolution of the fragile symmetry, and the red curve represents the evolution of the robust symmetry. And you see the red curve remains more or less constant over a long time. We also looked at the spin chain, just the Heisenberg spin chain for the unperturbed part of the Hamiltonian. And we just considered 4 spins, and we chose the perturbation in the initial state just randomly. And in this slide, epsilon is just 0.02. And this is evolution. Again, we can decompose any physical quantity into robust symmetry, robust conserved quantity, fragile conserved quantities, and off-diagonal components of the physical quantity. And this green curve represents the time evolution of the fragile part of the symmetry. And this red line represents the evolution of the robust part of the symmetry. And you see the red curve is more or less flat and very, very well preserved for a long time. And they say, so this Heisenberg chain has some integral charges, and we can look at the evolution of the integral charges. And for instance, you can look at the evolution of magnetization under perturbation. And the energy, of course, energy is a good, robust conserved quantity. And even under perturbation, it remains more or less constant. But the magnetization, it's, how can I say, popular conserved quantity for spin system. But this is unfortunately fragile symmetry, fragile conserved quantity. Okay, so this is a summary of my part, and so we found two different types of symmetries. So one type is a fragile symmetry, and the other one is the robust symmetry. And the robustness of the robust symmetry is based on the eternal adiabaticity of the evolution of quantum system, but quantum systems. And we have some bounds, explicit error bounds, and so on. And of course, I think I'm obliged to comment on the problems for this workshop. And I just prepared one slide. I'm sorry, just one slide. And yeah, so we showed some eternally valid adiabatic theorem and eternal valid robustness or the robust symmetries. And on the other hand, there are some fragile symmetries. This is our result. But we focused on the finite dimensional systems. And of course, we want to go to the infinite dimensional systems. And I know there are many trials, there are many attempts, there are many works for the establish a quantum version of the Kampf theorem for general infinite dimensional systems. And I think maybe in the following talks, Marilena might comment. Marilena's talk might be related to this subject. And maybe, so as I told you, for finite dimensional systems, not all the symmetries are robust. So some symmetries are robust, some symmetries are not robust. So maybe it's good to clarify what is the conditions for the robustness for infinite dimensional quantum systems. And another direction would be, so we actually, for finite dimensional systems, we also have eternal adiabaticity theorem for open systems. So we just consider GKLS generators, open system, constant time independent system. And we can do the same. We can prove the adiabatic, eternally valid adiabatic theorem for such a GKLS system. But there is some small problem. So we found an adiabatic evolution, so effective evolution respecting the block structure or the unperturbed part of the GKLS generator. But such a effective generator is unfortunately in general not GKLS. So the effective evolution respecting the structure symmetry of the unperturbed part of the generator is not a physically valid generator. So, and we have a counter example. So we have to give up the GKLS structure for the adiabatic evolution. But it would be nice to find a good, better, effective model because, as I told you, this is related to the modeling for the quantum devices. So it's better to find a good model or good effective model for general, how can I say, practical quantum devices. So it would be nice if we can find the physically valid GKLS effective generator, valid for eternally, valid for any long time. Okay. I just stop here. Thank you very much for your attention.